Hello everybody and welcome back to this tutorial on principal component analysis for data visualization and compression. Now that we have the iris dataset all set up, we've performed the elbow method, we can move on to the fun part. That is the principal component analysis itself. So what exactly is principal component analysis? It's definitely not immediately clear to me before I went and learned more about it. So for you guys who are first getting introduced to this, here's a little blurb from Wikipedia. Principal component analysis is a statistical procedure that uses orthogonal transformation to convert a set of observations, possibly correlated variables into a set of linearly uncorrelated variables called principal components. All right, so unless you have a pretty heavy background in linear algebra, you're not going to understand the background of principal component analysis itself, and that being the eigenvectors and eigenvalues that are used in PCA. Fortunately, implementing it with scikit-learn is relatively easy and straightforward. So we're going to demonstrate how to do that today and use it for a visualization and compression of the iris dataset. But if we look at this a little bit first, so PCA is best used on a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables. So what this is saying is that to start, we should probably have some features that are correlated to one another. And as a matter of fact, that is indeed what we have. If you go up here into our scatter plot, and I'm actually going to make this a little bit bigger so that we can see it. So I'll add a figure size here onto our original scatter plot. So there we go. We have many correlated features here. So for example, our petal length and our petal width show a strong linear correlation. These could probably be very easily compressed down into a single feature using a PCA reduction. So it could be reduced down to its principal components. And then the sepal width and the sepal length, those aren't as correlated as our petal length and width. However, they do show some correlation as well, so those could probably be reduced. And that is why this scatterplot matrix was so important to do in the first steps, because it shows us that we do indeed have a data set that has correlations among our different features. So this is a good candidate for PCA reduction. All right, and we are going to map that to linearly uncorrelated variables. So how exactly do you do this? Well, you start by saying from sklearn.decomposition import PCA. So this is going to give us our PCA class. And we also want from sklearn, we want to import pre-processing because we're going to have to do a little bit of that. So we've got that. Now what we can do is we can perform the, I'll just say PCA for principal component analysis. So PCA is going to equal to our capital PCA here. This is the class that we just imported. And number of components that we want to visualize this. So let's compress this down into two components that we can plot as an X and Y. So number of components equals 2. And then it's as easy as saying, I'll say PC for principal components here is going to be equal to PCA.fit transform our data frame. So this is going to take the data stored in our data frame above, the 4 different features, sepal length, width, petal length, and width, and compress it down into 2 components. And so let's take a look at that, and we'll print new dimensions, as well as print off a few of these for an example. So we'll say print PC. Let's print off the first 10 of these. This is no longer going to be a data frame. It's now just going to be an array. So that is why we have to index it this way instead of saying like head 20 as we did in the past. All right, so let's run this. So here we go, PCA. It's really quick. Simply using this scikit-learn PCA class, we have reduced our data set down into 2 dimensions here. So we have 150 instances still, but they only have 2 features now, and here are the first 10 of those. So they look nothing like the values that we had above the features in our data frame. So we even have negative values now. However, they've all been reduced down into these two components. So that's the data compression part of the PCA reduction. Let's actually now go on to the visualization of this PCA reduced data. Well, what we want to do first is we want to actually refit the k-means model to the principal components with the appropriate number of clusters. So the appropriate number of clusters was just determined with the elbow method. We confirmed that yes, indeed, 3 clusters will be good. And the principal components were obtained using the scikit-learn decomposition PCA class. All right, so to do this, we simply say k-means equals our k-means. Number of clusters equals 3. There we go. K-means.fit PC. So we're fitting it to the principal components, our reduced information here. And that really quick, there we go. Number of clusters 2. We fit it. We're good to go. We have our k-means algorithm. And now we can do the visualization. After that, we'll move on to perhaps clustering metrics and determining how well this k-means actually fit. But the visualization is actually going to tell that as well, because we're going to be able to visually see points that were misclassified. All right, so this is how you visualize high-dimensional data, in this case at least. So we want to visualize high-dimensional clusters using principal components. There we go. So we're going to use a mesh grid for this. So first we want to set size for the mesh. This is going to be like a quality of the mesh. It's going to be like a step size. So we'll say h equals 0.02. Depending on the resources available to you, you could make this lower for higher quality or higher for lower quality. Then we want to generate the mesh grid. And to do that, we define like an xmin and an xmax. So we'll say xmin, xmax is going to be our principal components. So our x from our principal components, so our minimum there, minus 1. So we'll get a little bit outside that. So PC, all of the instances, x dot max plus 1 for that. So minus 1 and plus 1, then our minimum and maximum values, and our x. We'll say ymin and ymax are going to be very similar. We'll take our principal components, all of our instances, but now we're using that second component, index number 1. So minus 1, we'll say. All of these, index number 1, max, plus 1. There we go. So there's our mesh grid. But we actually have to generate this using NumPy now. So we'll say xxyy is going to equal mp.meshgrid mp range xmin to xmax. And we pass to this mesh grid function here our h, which is our quality or our step size. And we'll use another range for the y's and pass it the same h. Okay, so we're good to go there. We have our mesh grid. Next, what we want to do, so this has a nice color scheme to it, let us label each point in the mesh using our last trained model. So label each point in mesh using last trained model. There we go. So z, those can be our point labels. We'll say k-means dot predict, and we'll pass to it our mesh grid. So we need to use a couple functions here. We have ravel, yy.ravel. Just a little notation here. This will label each of the points, so it's allowing us to do a k-means prediction on all of those. Then we can use that. We can generate the color plot from our results. And I apologize that we're actually going to do a pretty in-depth cell here, so we can't stop and visualize these. We're just going to go all the way through it, and then at the end we'll have the one graph result. All right, so generate color plot from results. So we need Z, but first we actually need to reshape this to XX shape. You could use YY here as well. Then we'll generate a PLT figure. We'll set a fig size so that we can see it nice and clearly. This is simply clearing any past data that you might have had in the PLT, such as perhaps an elbow method. So clear figure there. PLT.ImShow now Z interpolation we need to define. And I actually misspelled that. Interpolation, there we go. So this is going to be equal to nearest. We'll just do a nearest neighbor interpolation. We have extent we need to define. That's going to be the XX min, XX max, YY min, and then YY max. There we go. There's that. So there's our extent. We also need to do a color map, so this looks nice and pretty. We can just call a generic PLT color map. PLT.cm is the color maps, and then tab 20C was one that I picked out earlier. This one looks pretty nice. There's a lot of different color maps though, so if you want to play around with this, please be my guest and look through the PLT color maps. So aspect, we'll say auto, origin, lower. All right, so there's our PLT figure with our mesh grid of our results. Now what we actually want to do is we want to add to these the principal components. So we want the color plot with our principal components plotted on there. So what we can say, we'll do a comment here, plot the principal components on the color plot. And to do that, we can simply loop through these. We're going to have to use an enumerate so we can index them. So enumerate PC, our principal components. We'll say if target of I is going to be equal to 0. So if the target is 0, and this is actually going to allow us to color the different points. We can say plt.plot point 0 point index 1, so this is our x and our y, our first principal component and our second principal component. We'll give it a color, and then just for aesthetics, marker size equals 10. All right, so this is saying if the point, the target or the class label for the point is equal to 0, if we go up above here, that would mean that if it is a setosa iris, we're going to plot it as a green point. So we can actually do this for all 3 of our different classes. And we actually have to fix our indents here. So let's take that back. We'll say if target equals 1. So if it's on our second class, let's give it a nice red label here. The G and the R, those are referring to green and red. And then finally, one more. So we'll say if target of I is equal to 2, our third class, let's give it a blue marker. So that way we can see the actual labels for all of the points that we plot. All right, so we have our points, we have our color map on our color plot. Let us add onto there the cluster centroids so we can see the center of all of these clusters. So we'll say centroids is going to be equal to the k-means, and we can pull these directly from k-means model. Cluster centers, so there's our centroids, and we'll add them as a scatter plot. So we'll say scatter centroids. So for all 3 clusters, we'll plot the x. Centroids, for all 3 clusters, we'll plot the y. And then let's make these white x's. So we'll say marker equals x. That'll give it an x. And we'll say size, or just S here, is going to be equal to 250. Line width, we'll say equal to 4. Color, let's make these white. And then Z order equals 10, just so they show up on the front. All right, so there we go. If you want to format this, we can click and enter there just to put these on separate lines, make it look a little bit nicer. All right, and now we actually get to just simply set the plot title and axis limits. Always a good idea to label PLT title K-means clustering on PCA reduced iris data set. All right, it's a nice descriptive title. PLT.xLimit. Let's just say xmin, xmax. PLT.yLimit, ymin, ymax. There we go. There's that. PLT.xLabel. This is your principal component 1. We'll just call it PC1. PLT.yLabel is going to be your principal component 2. All right, there's that. Let's take off the tick marks since we really don't need them here. PLT.yticks. If you just do an empty set here, this will remove the tick marks. All right, and so what's that last step again? PLT.show. Always got to call the PLT.show. All right, so let's see how this looks. Bearing no spelling errors, which some of you may have seen, we should be good to go. So Shift-Enter. This will run really quickly. And down here we have our plot of our PCA reduced iris data. And so here you actually see the 3 different clusters, centroids, with our white X's. You see all of our PCA reduced data denoted by the different points. And you actually see the locations in the color map where the clusters separate. So that's what these lines here are actually denoting. So you see here, this point, for example, since it's red, it actually belonged to this class initially. However, it's in the location of this other cluster, so it's actually been misclassified. And these blue ones down here who belong to this centroid, they have actually been misclassified as well. So you see some errors. We've got some obvious errors right away that we can see from our visualizations, but you also see that we have pretty good separation of clusters for this other guy. So this first class, or this first cluster, very separable, while these other guys get intermingled a little bit more. So that is why we're going to get some errors from here, but we're actually classifying all of these ones perfectly correct. And so you can play around with this plot. That is the good thing that you can do now. For example, let's come up here and see if we do get an advantage from going to that 4 clusters. So if we refit with 4 clusters, we can just come down here and run this again and see how it changes with that 4th cluster. So actually not that good. It doesn't look like this is helping us much at all. You've got a lot of misclassified. And in fact, this class here is really just 50% both of these other guys. So not worth it to go to 4 from 3 clusters. So we'll go back down. And here's our visualization. So it's hard to actually say, for example, why these 4 features that we looked at above are descriptive enough to separate these different clusters. However, if you do a visualization like this, you can say, look, there is a clear separation of this cluster in the PCA reduced data, and this clustering or this separation is also going to be reflected in the higher dimensional feature spaces, and as a result, we can cluster this data successfully. So if you needed to explain why you had to separate, or why you could separate this data or cluster, this could be a good visualization to do that. All right. So this is nice. It's pretty, but we do see we have some misclassifications here. So let's take a look at some cluster metrics just so that we can see how our algorithms are performing, and then perhaps where we went wrong. So what I'm going to do is I'm going to copy in a little bit of text here. This is going to be be 3 metrics that we are going to use today to classify the success of our clustering. We're going to use homogeneity, which is going to measure whether or not all of the clusters contain only data points which are members of a single class. So for example, this cluster would have a homogeneity of 1. However, these guys, since they have data points belonging to different classes, aren't going to be completely homogeneous. Completeness, very similar. However, it's looking from the opposite perspective. It measures whether or not all members of a given class are elements of the same cluster. So all of these guys, the green points, are all in the same cluster, so completeness 1 for them. However, these guys are going to be a little bit lower. V measure is a harmonic mean between the homogeneity and completeness. So this is just combining both of those into a single score. So let's take a look. So from sklearn, we want to import metrics. We'll say k-means clustering on non-reduced data. So what I want to do is compare our clustering performance on our reduced data versus our non-reduced data. So we'll say k-means 1 equals k-means number of clusters equals 3. There we go. K-means 1 dot fit. So features. This is our data frame before it's been reduced. And then down here we can say k-means clustering on PCA. Oh, I've got some capitals here. Reduced data. There we go. So to do that, we can say k-means 2 equals k-means number of clusters 3 again. Keep that consistent. K-means 2 dot fit PC, our principal components. All right, and let's print off these metrics. So what we're going to do is we're going to print metrics for non-reduced data. So first, let's print off non-reduced data, so we know what we're looking at. Next, we'll print our homogeneity, and we'll substitute in using the dot format this variable. Simply going to be metrics, which we imported above, dot homogeneity underscore score, our target, k-means 1 dot labels. Print completeness dot format. We'll substitute in metrics dot completeness underscore score, and we'll pass to it as well the target and the k-means 1 dot labels. All right, there we go. There's that. Last but not least, we're going to print off the V score or the V measure. Format metrics, V measure score, target, and then pass to it the k-means 1 labels. All right, there's that. A little bit tedious to type it out, but don't worry, we can simply copy this. We're going to go down here and we're going to paste it, and we're going to do this for the PCA reduced data. So we'll change some things here. So we'll say PCA reduced data. And instead of k-means 1, what we actually want to switch here is to the k-means 2, since that is indeed our reduced data that we're fitting on over here, our principal components. All right, and we look good, so let's go ahead and run this. It goes very quickly. So for the non-reduced data, we're right around 0.75, 0.76. And you actually do see that for the PCA reduced data, we actually get slightly worse. So it looks like we introduced maybe 1 or 2 more misclassifications in the PCA reduced data versus the non-reduced data. And this, in general, is going to make sense. You're doing a PCA reduction, you're compressing the data down, and as you compress the data, you lose a little bit of information. And as a result, you're actually not able to cluster it quite as accurately. However, these scores are very similar, so we are still retaining a lot of the original data in our PCA reduction. So you can say, indeed, yes, this is still doing a pretty good clustering. And this is going to be dependent on, once again, how well those original features correlated with one another. You want to make sure that you have similar clustering between your non-reduced data and your PCA reduced data, because otherwise your PCA data isn't going to be worthwhile. If you lose all of your accuracy in your PCA reduction, it's not worth it to use it for the k-means clustering. However, as we just verified here, we're actually pretty similar between the non-reduced and the PCA reduced data. So this visualization is going to be relatively accurate and similar to the clustering that we would get for our non-reduced data. So let's actually just print out some of these labels so we can compare the results visually. So compare results further, print out the actual labels. We'll say simply do a print k-means 1 dot labels underscore print k-means 2 dot labels. And let's actually print out the target, so the actual labels that we had. And so one thing to note with this, as we print this out, these clusters are assigned random numbers. So for example, we have a 1 here and a 0 here. However, these are referring to the same data points. And as you can see, this is going to be this first cluster here, all these green guys. And both of these are getting all of those exactly correct. Even though they have different cluster labels, remember, this is unsupervised learning. We don't know the actual labels, so we're just assigning a integer to these different clusters. And if we actually run this a couple times, you'll see that they change depending on what it gets assigned to. So if we run it enough, eventually you would get it to where they assigned it the same. But it doesn't appear that we're gonna, so that's okay. All right. So you do see here, though, that there is some misclassifications in this second cluster, and there is also some misclassifications in this last one as well. Just some mix-ups between the 1s and 2s here based on our actual labels, but relatively pretty good. All right, so that's actually going to bring us to the end of this project. Let's just go over really quickly what we were able to accomplish today using the IRIS dataset, which we are importing directly from sklearn. We built a data frame. We displayed correlations amongst features in our original dataset. We showed, all right, yes, since there are correlations, this is a good candidate for PCA reduction. We also used the elbow method to determine the optimal number of clusters to use for k-means clustering. We actually probably knew what this was gonna be. It is indeed 3, since we have 3 species of clusters here. But this elbow method, very useful in k-means clustering and unsupervised learning in general. We then did a principal component analysis, and we used it to compress our data from 4 dimensions to 2 dimensions, or number of components 2 here. So we reduced our data, we did data compression, and then we fit our k-means model to that reduced data, and we were able to visualize it as a 2-dimensional plot, since we reduced it to 2 components, to just visually see the separations of clusters that we are getting in this data. And we also validated that we were, it was all right to use this approach because we showed similar homogeneity, completeness, and V-measure scores between our non-reduced data and our PCA reduced data. However, we did see that we are losing some information when we go to the PCA reduced data. And we did a visual inspection of the labels. All right, so I hope you learned a lot. I hope you can use that elbow method in future implementations of k-means clustering on your own data. And I hope this visualization helps to show how PCA can be used to take high-dimensional data and plot it in a format that is easy and viable for humans to see. So that brings us to the end. Thank you very much for following along, and I will catch up with you on the next project. Thank you very much.